And if this has to maintain equality, if the left side drops, that side has to drop. And if you can't control these two, the only thing that can happen is what? Temperature has to drop, right? So you actually see this, well, you know what? You also see it, like these last few months have been pretty hot in San Antonio, right? And we all use air conditioners, right? You get in your car, you crank it up. So what's happening there? You just turn on, who cares, right? Just give me cold air, right? It's this same sort of idea here. What's happening is, I'm not going to get too technical, because I'm also not like a professional air conditioning whatever person, all right? But I do know basically how an air conditioner works. What you have is this stuff called Freon. Heard of that? And this Freon can be both in a liquid and a gas form. But the short story here is this. You turn on your car, you turn on the air conditioner. What happens is you start pumping this Freon through a system. And as the Freon goes through this tube, okay, your Freon's moving through this tube, there's a small little orifice, this tiny little hole. And what happens is as it gets pushed through that hole on this side of the hole, it's very, very high pressure. And then on this side of the hole, once it's sprayed through there, it's very low pressure. So what happens is that you have a major pressure drop. And when the pressure drops, the temperature drops. So the Freon coming out of this side is cold, 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 all right? Now it's still inside of a tube, but it's no pressure here, high pressure here. So this is, warm Freon goes through, gets sprayed out here, comes out cold, right? Then this pipe runs like this through this like serpentine, and then you have a fan behind it. And that fan blows over these cold pipes, and that creates your cold air, all right? And then what happens is this goes, all the Freon that came out of here that was cold now comes around, goes into like this, that's a terrible tank, goes into like this tank, okay? And then it goes through a pump and gets pushed back through, and there's just this cycle, all right? That's how your air conditioner works. But it's all based upon this basic ideal gas law. Pressure drops, temperature drops. Pressure increases, temperature increases. So, if you have a very, very small change in pressure, right? What if the pressure changes just a little bit? How would that impact temperature? Like, if I change this pressure by like 1 unit, does it change the temperature by 1 unit? If I change the volume by like 1 unit, does it change the temperature by 1 unit? If I change the temperature by 1 little unit, does it change these by 1 unit? What's the relationship in the way they change? Do you think it's 1 for 1? Do you understand what I'm saying? Drop the pressure by like 1, does the temperature come down by 1? We would like to know that, all right? And the great thing about implicit differentiation is that you can use it with any equation. Any equation. So what we're going to do right now is I'm going to take this, and I want us right now to find dP d little t. Okay. So I said here capital T is temperature, right? Capital V is volume, capital P is pressure, and these two are constants that you don't have any control over. You don't get to move, you don't get to change those. What I'm asking you right now is how much pressure changes. You know what, let's do capital T. Sorry, let's just do capital T to start. This is probably going to be the only thing we have time to talk about. So what if I ask us to do this, right? How much does the pressure change if there's a little change in temperature, all right? All right, so let's see if we can apply what we learned before. We have an equation, and I'm going to now take the derivative on both sides of this equation with respect to what? Temperature. Capital T, temperature, right? So I'm going to take the derivative with respect to capital T of the left side equals the derivative with respect to T of the right side. Right? We want to find how the pressure is going to change if I make a small change in temperature. This should tell me exactly how it's going to change. All right, how do we take the derivative with respect to t of this? Product rule, right? Look, we have a product there. We have a product. So we're going to take derivative using the product rule. So what is the derivative of p with respect to t? dp dt, right? So that's derivative of the first one, then times what? The second one, v, plus, now, the derivative of v with respect to capital T, which is dv dt. We actually, it's not one, right? It's because v and t aren't the same variable. So it's dv dt times what? P. So that's our product rule. Are we done on the left? Yes. Equals now the derivative with respect to t of this side. Now you might be thinking triple product and start getting sick. However, n and r are constants, aren't they? So they just come for the ride. And then all I need is the derivative of capital T with respect to t. So it should just be 1, right? Plus, times the constants. So just n times r. Any questions on that? Okay, so what were we trying to find? dp dt, right? You see it in there? Okay, let's isolate it. So I'm going to move this guy to the other side. So dp dt times v equals nr minus dv dt times p. Okay, so I just moved this one to the other side, right? Last step, divide everything by v. dp dt equals nr minus dv dt times p, all of it over v. All right, so let's try and interpret what this answer is telling us. This is the ideal gas law, okay? That we can't change. That is a law. We don't get to manipulate that. That's the way it is, all right? So if I ever want to know the rate at which the pressure is going to change with respect to changes in the temperature, here's what I need to know. I need to know the number of moles and Avogadro's number. I need to know that, which I should know, all right? I need to know the pressure in the tank, okay? I need to know the volume in the tank. And there's one more thing I need to know. What is it? The rate at which the volume is changing. So I've got to be able to measure those things somehow. So if I can measure the pressure and the volume and how fast the volume's changing, then I should be able to tell you how fast the pressure's changing. All right? I can't really get more into this because this is leading us into the next section, but the big takeaway that I want, or the thing I want you to take away from this, that is the profound idea here, is that this works with any equation out there. This has always blown my mind. It still blows my mind to this day. Go grab me a physics equation, grab me a chemistry equation, go grab me a biology equation. No matter what the equation is, I can always tell you how those variables change with respect to one another by using implicit differentiation. I can always do it. We can always do it. And that whole process is going to lead us into the topic for the next class, which is called related rates. Related rates. And this historically is top 2 hardest sections in the book, is what most Cal 1 students tell me. Is like, if there's something from Cal 1 that you hate or didn't like or didn't enjoy, related rates is usually on the top of the list. And it's because it's word problems and implicit differentiation. So, but you can see hopefully from this equation that we came up with, right, after we differentiated, that somehow this is a rate of change, right? And this is a rate of change. And somehow they are related to one another, right? They are related rates of change, related rates. And so we are going to study those more. But we'll have like a word problem behind it instead of just, let's just do this. All right, talk about the test, yes? All right, you have a test on Thursday. Okay, that's it, right? So what do you want to know? What should you do to prepare? Well, of course, do your homework, right? Make sure you review your homework. And I talked last time about, trying to give yourself that testing scenario, right? I looked at a couple of versions of tests from the past before I came to class. Guaranteed, I'm going to give you a problem where I draw a picture of a function, and you have to draw me the derivative. All right, so we did that in class. Something like, if I gave you this function like that. There was a set in the homework where you had to do this, and you had to play a matching game. So you say, here's f. What does f prime look like? Yes? Sounds right. Yeah, 2.2. Yes. Yep. Oh, wait a minute, hold on. Yes, it is. Okay, so, but see, in 2.2 in the homework, they gave you f, and they gave you a bunch of the pictures of the derivatives, and you matched. You matched them. On the test, I give you f, it's no matching. You draw me f prime. Okay, so if I were to draw f prime here, what would the derivative of this thing look like? What can you tell me about between here and here? The slope of the tangent line is always constant, so the derivative is constant, and it looks like the slope is about what? Maybe 1 or so? So I know that it's going to look like this. The derivative is going to be constant until you get to about here. And then what happens once you get there? The slope is negative and constant, so it's going to all of a sudden become negative and go like that. And then once you get to a certain point, like right around here, it's going to switch back to positive. So that would be what the derivative looks like. So I just go back and review these, all right? So if I were you, I'd look through 2.2. I would do the matching, but try and do it without the other side. Just take each one of them, try and sketch them, and see how you do. Remember that these pictures don't have to be perfect, all right? When you draw these, it's just a general basic idea of what's going on. Okay? Also, I'm going to ask you to find f prime of x using the limit definition. So that means I want you to find the derivative without using the shortcuts, which means you have to use that definition, f prime of x equals limit h goes to 0, f of x plus h minus f of x all over h. I do not intend on giving you that formula because you've all memorized it by now, so there's no need for me to give that to you. Yeah? Make sure you know it. Remember, if you have trouble memorizing things, as soon as I start the test, if you want to write that down on the test, just write it down. You only have to save it for 30 seconds or so, right? Okay? So I will give you a function. Now, the good news is that the function I give you is going to be something nice, like the algebra is doable, okay? Which means you can check your answer using the shortcuts. Yes?
Do I have to find the slope again, like when we use the definition?
Do you have to do what?
Find the slope, like use like y equals 1, y1 equals m.
Okay, so the question is, if I ask you to find a derivative using the limit definition, would that be part of a bigger problem where I ask you for the slope of the tangent line at a specific point or the equation of the tangent line? So those are two different things. Make sure you understand the difference. If I ask you for the slope of the tangent line at a specific point, you only have to find the slope. If I ask you for the equation, you have to find the line. Y minus y1 equals m times x minus x1. On every problem that you could imagine doing on this test that involves taking the derivative, you should always be able to find the equation of the tangent line, always. So I would definitely make sure you study the problems in your homework where they ask you to find the equation of a tangent line. Also make sure you study the problems in the homework where it says, you know, they give you a function, they say, find where the tangent lines to this function are horizontal. Something like that. What does it mean? What is that question really asking you to do? Take the derivative and set it equal to 0. Because they're trying to figure out where the slope of the tangent line is horizontal, which means it has a slope of 0. So you're actually setting the derivative equal to 0. And that was in the homework. I know for sure that's in the homework. All right, so let's recap. Picture, you draw me the derivative. Take a function, do the derivative old school way. And you know, an example of something like this would be maybe, I don't know, I don't see myself going any crazier than like maybe a cubic function. I mean, that would be the worst I would probably do to you. Like that would be pretty painful, but that would be about as bad as it would get. Ask you to use that definition. You can check your answer, right? You can check your answer because at the end of this, you know that it should be 9x squared minus 8x. That's your answer at the end. But do not just put this down, right, and box it, because you'll get basically no points for that. Because I'm telling you, using the limit definition, you have to do this. All right? Then later on in the test, I'll ask you to find some derivatives. I'll just say find the derivative, you know. If I do that and I don't put this, that means all the shortcuts are on the table. Okay? And those shortcuts are on your formula sheets, most of them, right? All your derivative shortcuts are there. Right? Yes. So, you know, make sure you just kind of go back and go through the sections. Like the first thing we got was the power rule, right? Make sure you can do the power rule. One of the problems that always trips up students, and this kind of, it drives me crazy a little bit. I don't get driven crazy much, but this does drive me crazy. I'll give students a problem like this on a test. X to the 4th minus 3x squared minus the square root of x plus 1 over the cube root of x. And I'll ask them to find the derivative. And you don't know how many students do the quotient rule on that. I think, like last semester, I think almost every single student did the quotient rule on that. So why does that drive me crazy that students do the quotient rule on that? Yeah, I mean, this is the case where you have a single term down here, right? And so what you can do is do this over this, this over this, this over this, this over this, write them out separately. Then they're all going to be powers of x, and then just use your power rule. Right? Like, if you put this over this, that'd be x to the 4 minus a third, because you just subtract the power, right? And then you take derivative of that. That's much better than the quotient rule, because what students will do the quotient rule will just look like a disaster of a mess. And it takes them like 3 times the amount of time to do it. So review that section, power rule. I envision on this test a lot of problems where I say find the equation of the tangent line. Right? So I give you, let's say I give you this right here. And I say, you know, there's that function, find equation of the tangent line at, and then I give you a point, right? So what you have to do first is find the derivative, and then you plug in the x value into it to find the slope, and then you y minus y1 equals x. Yes.
But that definition, you don't want us to use that one definition you drew and not the other one, and you know where f of x minus f of a over.
For the limit definition?
Yeah, for the limit. I know
There's two. You can use the other one if you like, if you are partial to it. Okay, so we've got basic power rule, and then after power rule, what do we have? Product rule, right? Then we have quotient rule, and then the almighty chain rule, right? And you can see with the implicit differentiation that we did today, there's like you don't survive without chain rule. You have to understand it. So after chain rule, we have implicit differentiation. That's what we've been doing today in the previous class. So that's it. That's all that's on the test. Does it seem like a lot? Yes.
I know it depends on the question, but would you recommend us using like the product or quotient rule or using a chain rule? Or could we use
The problem's going to dictate that to you, right? Each problem, when you look at it, is going to to determine by what it is in front of you which rule you're going to use. Like if you have a problem like like this, has to take derivative, you don't have a choice. You have to use chain rule here, right? You don't get to use product rule because that is not a product. So I think the problem itself is going to dictate to you which method. I think that's pretty much... Oh, be able to find second derivative, perhaps, right? Maybe not, I mean, not as bad as what we did today, but if I ask you for a second derivative, you shouldn't like freak out. Also, remember, you need to know the derivatives of all the 6 trig functions, right? Which are in your formula sheets, right? Derivative, sine, and cosine, tangent. One of the ones that gets students a lot is, I'll give you an example right here of a mistake students make all the time. I shouldn't say all the time, because it doesn't happen all the time, but it happens a lot. Give a student like this, okay, and ask them for the derivative of this, okay? So what I get a lot is this. I get that a lot. So the student says, okay, I need to take the derivative of secant of this, right? And so they look at their formula sheet, and this formula sheet says secant x tangent x. So they write down secant x tangent x, and then they say, oh, chain rule, now I need derivative of that. What's wrong with this? Yeah, these arguments are not x. These arguments are actually that, right? So this should be secant of x squared plus x, tangent of x squared plus x, then the derivative of what's inside. I see that more often than I want to. Any questions? Because we're down to the last minute or so. Yes?
So with the x ones, like we have a question where, like, I think we did always go get fx equals x cosine x by f to the 400.
Yeah, that problem, I think that would be more along a bonus question. The question was about, you know, like finding the 150th derivative of x cosine x. Yeah. Yeah. Any other questions? So you can have your formula sheets. That's pretty much all I'm allowing you. So don't go modifying them with your favorite formulas on them. Just. And then next, on Thursday, I'll be in my office before class. I'm there, usually there by 9:30, 9:30-ish. Okay? So if you want to come by and talk about anything before the test, I'll be there. All right, happy studying. I'll see you on Thursday. Make sure you sleep, make sure you eat.
Why did I do that song? Why did I do that?